All right, we got a new term here. This is polyprotic acids. Now, if you break down the word, you can probably figure out what a polyprotic acid means. Poly meaning many, right? So you know this means many. Protic means protons, or we're talking about acids and bases, so that's like H plus, right? So this is an acid with multiple H pluses. Okay, so essentially definition is it contains 2 or more acidic hydrogens or H plus. Essentially that means ones that can come off or can act like an acid. Okay. Now, one thing to know is that these will dissociate stepwise, meaning one comes off and then the other comes off. So like you have two separate equations. So remember I said you're always going to have 1-to-1 for acid base. That is still true. You only take one hydrogen off at a time. They actually have different Ka values and everything. All right. So common polyprotic acids, I already mentioned one in an earlier video, H3PO4, I'll use a lot. Carbonic acid is also a really common one. So you'll see me use these for examples. So I did say that there's successive steps. So they have separate K values. So you only take one hydrogen off at a time. So I'm going to use carbonic acid as an example. If I said write the Ka equation for carbonic acid, you would be like, okay, H2CO3 plus water. This is a weak acid, so I got equilibrium, loses an H. Now I'm left in HCO3 minus, still has one of the hydrogens on there, and H3O plus. Okay, so I only took one hydrogen off. Now I was left with HCO3 minus, that can lose another hydrogen. So my second step would be starting with that, again, adding a water, weak acid, losing the second one, I end up with CO3 2 minus and another H3O plus. Now these have, like I said, separate K values. We call this one Ka1 and this one Ka2. The first one, the actual value is 4.3 times 10 to the negative 7th. This one is 5.6 times 10 to the negative 11th. So you can see that the K values get smaller as you go on. Each hydrogen is more and more difficult to remove. So that means as you go on, Ka gets smaller. Okay, it's always easiest to take off the first hydrogen, harder to do a second. And if there is a third, even harder to do the third. So it may not act acidic like at all. All right, so we're going to do an ice problem that has to do with a polyprotic acid. Okay, it says, what is the pH of a 0.050 molar carbonic acid solution? What is the concentration of carbonate, excuse me, at equilibrium? All right, so break down this problem, see what we got. What do we need to find? I want to know pH. That means I need the H plus or the H3O plus concentration at equilibrium to find that. pH goes with H plus, okay? 0.050 molar HCO3, that means that's what I put in initially for H2CO3. And then I want to know the concentration also of this at equilibrium. All right, so let's look at this. Remember, take one hydrogen off at a time. I'm going to write my first equation, H2CO3 breaks into H plus and HCO3 minus one hydrogen at a time, right? I didn't write out the whole water equation because you don't need the water part, okay? So I started with 0.050 of this, 9 minus x plus x plus x, 0.050 minus x, x. All right, so I already told you Ka1 for this was 4.3 times 10 to the negative 7th. You can look that up on your sheet as well. That's going to equal x squared over 0.050 minus x. Awesome. I'm going to drop this guy. Then weak acid, it's probably okay. X is, after I calculate, 0.000146663. Definitely less than 5% of 0.05. So I'm good. Okay, so that is actually this value and this value. So notice I asked for the pH at equilibrium. Well, I haven't completely broken down the carbonic acid yet. So I need to do a second ice table. So any polyprotic acids actually need as many ice tables as they have hydrogens. So we are going to do a second ice table with the second Ka. So before I calculate anything, that HCO3 minus. This one's going to give me also an H plus, and now I'm down to CO3 2 minus. This is important to do because, yes, I did also want that concentration at equilibrium. So got ice here. Now, what do I put in my initial? Well, my initial has to come from the first ice table because I didn't actually put this in, but it's in there. So that at the end was X. So this is actually the X value that goes here, 0.000146663. That's how much I had initially from the first ice table. I also have H plus initially, so I need to put that in here, 0.000146663. Now I know we haven't had concentrations in the product side yet, but it is possible, all right? So I have that there. I do not have CO3 2 minus from the equation above, so that one is 0. So this is still going to go to the right. It's not like we're trying to decide which way it's going to go because there's a 0 on the right side. You can't have a negative polarity. So this is still minus X plus X plus X. I got 0.000. Yes, I kept a lot of significant figures. 0.000146663. And this, plus X. And that one is just X. All right, so I'm going to do my Ka2 over here. Ka2, I told you, was 5.6 times 10 to the negative 11th. So that's going to be, this one's going to be a little bit longer, right? Products over reactants. So 0.000146663 plus X times X. So those are my products over my reactants, 0.000146663 minus X. Ooh, that's a pretty complicated algebraic problem. But this one is super weak. I can drop this and this. Drop that. Drop that. And then you'll notice that my concentrations actually will cancel out that 0.0014663 I have on top and bottom. So X ends up being my Ka2 value, 5.6 times 10 to the negative 11. Now I can plug this in here and here and here. I got my X value. Now 5.6 times 10 to the negative 11th is definitely less than 5% of what I started with and that HCO3 minus problem. So I'm totally good to drop it. Again, usually going to be good to drop it. Okay, so I got my X value. Now, what is the question even asking for, right? It wants the pH and the CO3 2 minus. So I needed this to calculate pH because that's my H plus at the end of this whole equilibrium thing. And I also want this value. All right, well, that's easy. That one's just X. So the answer for CO3 2 minus concentration is 5.6 times 10 to the negative 11th molar. It's just X. Okay, now I also wanted the pH. Now, if you notice, if you add 5.6 times 10 to the negative 11th to 0.0014663, that 5.6 times 10 to the negative 11th is not going to make much of a difference. So you can take the pH of 0.0014663. So pH is just going to be negative log of 0.000146663. Now, if you want to type in the plus X part, go for it. It's not going to make a difference. Your pH is going to come out to be 3.83. Okay, which makes sense for weak acid. All right. So I know that was a lot of work, but I did 2 ice tables. I had to find my H plus at the end and my CO3 2 minus at the end. And I could drop all of my X's.